Hello everybody. So in this video we're going to begin with Chapter 7, Statistics. And these are the learning objectives of this chapter. So by the end of this chapter, you should be familiar with the following: concepts of population, sample, random sample, and frequency distribution of discrete and continuous data, reliability of data sources and bias in sampling, recognizing sampling techniques and their effectiveness, interpreting outliers, presenting data using frequency tables and diagrams, as well as box and whisker plots. We're going to be working with group data, mid-interval values, interval width, upper and lower interval boundaries, and frequency histograms. Interpreting and calculating mean, median, mode, quartiles, percentiles, interpreting and calculating range, interquartile range, variance, and standard deviation, interpreting and calculating cumulative frequency graphs, and using them to find median, quartiles, and percentiles, interpreting and calculating linear correlation of bivariate data, and interpreting and calculating linear regression models. In the next slide, you're going to find an example of a graph that represents data pertaining to worldwide population health in UN member countries. One of the indicators that is reported is something called the Health Adjusted Life Expectancy, known as HALE, H-A-L-E. And this is based on life expectancy at birth, but it includes an adjustment for time spent in poor health. It is most easily understood as the equivalent number of years in full health that a newborn can expect to live, based on current rates of ill health and mortality. According to the World Health Organization rankings, years lost due to disability are substantially higher in poorer countries. Several factors contribute to this trend, including injury, blindness, paralysis, and the debilitating effects of tropical diseases. On the countries ranked by the World Health Organization, Japan has the highest health life expectancy of 75 years, and the lowest ranking country is Sierra Leone with 29 years. So in this case, we see here the average years: 70, 60, 50, 40, 30, etc. And on the left-hand side, we can see the frequency, which is based on the amount of countries with this health-adjusted life expectancy. One of the concepts that is most important in statistics is the concept of population. So population is the entire collection of people, animals, plants, or things from which we may collect data. It is the entire group we are interested in, which we wish to describe or draw conclusions about. In order to make a generalization about a population, we need a sample. And a sample is meant to be representative of the population. For each population, there are many possible samples. Okay, so we begin with section 7.1, Graphical Tools, and we're going to talk about classification of variables, which is another name for data. So data can be classified into two main types. It can be quantitative or numerical, or it can be qualitative or categorical. So what is qualitative or categorical? Well, the brand of a camera, opinions of voters, gender, etc. Quantitative or numerical is split into two subcategories. We have discrete data, which is things like number of children, houses, accidents, so whole numbers. And then there is continuous, which is things like length, age, height, weight, time, etc. Suppose a consumer organization is interested in studying weekly food and living expenses of college students. So there's a survey of 80 students that yielded the following expenses to the nearest euro. So here we have a table with the weekly food and living expenses for college students, 80 of them. So the first step in this is how to summarize the data. So what we're going to do is study something called frequency distribution. Okay, so here we have a frequency distribution table. And the frequency distribution table is used to organize data. Classes or groups are the numerical intervals for a variable being studied, and each class in the table shows the frequency or number of observations. Intervals are normally of equal size, must cover the range of the sample observations, and are non-overlapping. Non-overlapping means, for example, that if you take a look at the living expenses from 35 euros to 40, notice that it says equal or greater than 35, but less than 40. In the next class, we start at 40, and it will be less than 45, and so forth, right? And here we have the number of students, which is the frequency of the samples. Also to the right, we have percentages, which is simply the percentage of students out of the 80, right? So 2.5%, two students have living expenses between 35 and 40 euros. So in the next slide, we have an example of a histogram representing the data that was collected. So notice that on the y-axis, we have the frequencies. So this is the frequency of students and their expenses. Now, in this case, the width of the boxes represents the class. So remember that the first one we had was from 35 to 40, and they have put here the midpoints or the averages of those classes. And the height, again, of these bars is the frequency or the amount of students with this range of expenses. So next we're going to take a look at a table of cumulative and relative cumulative frequency distributions. So a cumulative frequency distribution contains the total number of observations whose values are less than the upper limit for each interval. It's constructed by adding the frequencies of all frequency distribution intervals up to and including the present interval. And then we can see that here, the cumulative number of students is simply an addition, right? So first we start with 2 students, and then in the next interval we have 3, so that adds to the 2 for a total of 5. And then the next interval or class has 11 students, so now it goes up to 16. And then the next interval has 21, so we add to 37 until we get to the number 80. Same thing with the percentages. So we start with 2.5%, then we get 3.75% in the next class, add that to the 2.5 and we get 6.25. And then from here we go to 13.75, which is the next class. So that makes it 20% and so forth. So here now we have a cumulative line graph or a cumulative frequency graph. This is also known as an ogive, and it's a line that connects the points that are cumulative percentage of the observations below the upper limit of each class in the cumulative frequency distribution. So this is the upper limit, and this is the percentage accumulated below that limit, right? And then what we do is that we simply translate those frequencies on the y-axis and the expenses on the x-axis, and then join the dots. So next we have example 7.2. And it says, the World Health Organization data discussed in the introduction is given here in raw form. A, prepare a frequency table, starting with a lower class boundary of 20. Well, this is wrong. It shouldn't be 20. It's 25. And a class interval of 5. So what that means is that you would have to grab all this data that is in raw form here and classify it according to each interval or class, and you would also have to have the frequency of numbers that are within that class. So what you should get is something similar to this table. Notice that on this left column, you have the life expectancy, and they call it L, and you have each interval or class. So we start at 25, and it goes from 25 to 30. Notice not including 30 because they're not supposed to overlap. So there's one country that has a life expectancy between 25 and 30. Then you would have from 30 to 35, where you have 4 countries with a life expectancy between those numbers, and so forth. So once we've done part A, we will be ready for part B, where they ask us to draw a histogram to represent the data. Now for that, we're going to use the GDC. Okay, so here we are with the GDC, and we're going to learn how to graph a histogram. So the first thing we need to do is click on Stat and Edit. And notice that I've already introduced the data. So in list 1, what I have is the midpoints of each class. So remember that the first class was from 25 to 30. So I've entered the midpoint, which is 27.5. The next one was from 30 to 35. So that should be 32.5. Let me correct that. 32.5, which would be the midpoint between 30 and 35. Then all the midpoints henceforth. And then on list 2, I'm going to put the frequencies that are related to each class. So from 25 to 30, remember it was one country, then 4 countries, 14, 14, 11, etc. Next, we have to make sure there is nothing in y equals. There should not be any function here, otherwise you're going to get errors. Next, we're going to click on second, and we're going to go to stat plot. And we're going to go into stat plot 1 and make sure it is on. So click on enter to make sure it is on. Then you go down to type, and you're going to pick the third type from left to right, which is a histogram. Then the X list is going to be list 1, where we had the midpoints of each class. And for the frequency, we're going to use list 2. You can also choose a color. If you scroll down to color and just use the arrows, you can pick any color you want. So we're going to pick green for this case. The next thing you're going to do is click on zoom and make sure you click on number 9, zoom stat. And there is the histogram. But we're going to adjust the window to the information that we need. So let's go to the window and notice that it has an X minimum of 27.5, which was the first piece of information we entered, but let's make that 25. Make that 25, and then the maximum was 80. So let's click on 80. The width of each bar is going to be 5 years, the class, so we have to make sure that the scale for X is 5. Now the Y minimum does not need to be a negative number, we can just start at 0. And then the maximum is 63, that means the amount of countries that are in one class. A maximum would be about 63 countries, but it's probably less than that, so let's use 60. And then we're ready. We just have to click on graph, and there's our histogram. Now if you click on trace, it's going to take you to each one of those bars. So notice that we have the first class from 25 to 30, and there's one country. Then we would have 4 countries where the life expectancy is between 30 and 35. Then between 35 and 40, we have 14, and so forth. So let's look at the largest bar, and that's between the ages 60 and 65, with a frequency of 54 countries. So that is the most common adjusted life expectancy according to the World Health Organization. And if we scroll all the way to the right, we will see the case of Japan, where the life expectancy is between 75 and 80 years, and that's why we have one case only there. So now we will do part C, which says draw a cumulative frequency graph to represent the data. And again, to do this, we're going to make use of the graphing display calculator. So Supposing it's all set up correctly, what we want to do is go back to Stats and go to Edit. So one thing I did was erase the previous list. If you want to erase a whole list, you have to put the cursor on the list itself and then hit on the clear button. So what I did is that in list 1, I put the upper bound of each class. So 30, 35, 40, 45, 50, etc. And then in list 2, what I did is that I put in the frequency for each one of those classes. So there are the frequencies. And now what I'm going to do is that I'm going to calculate the cumulative frequency, but I'm not going to do it manually. You already know how to do it manually. So how do you do it? Well, you go and click on second, and on top of stat, there's something that says list. And then move a little bit to the right, and it says operations. You see that? And notice that number 6 says cumulative sum. And then what we do is, since we want the cumulative sum of list 2, we go second and 2, and it interprets it immediately as list 2. We close parenthesis. Then we click on this button, which is store, and it's on the left-hand side of number 1. And then we want to store it in list 3. So we go second and 3, and then hit enter. Let's go back to the table. So we go back to stats and then edit, and notice that here we have the cumulative list. So the addition is already done for us. And there is the total of data points, which is 192. That is correct. So now we're going to graph this. So we go to stat plots and we click on 1. We make sure it's on. So enter. And then here we choose the type of graph, which you want is a continuous line. So hit enter. Now the X list, we want it to be list 1. So we go second key and 1. And the Y list would be the accumulated frequency, which we got from 3. So I think we're all set, and we can just click on graph. And it looks like it's out of the picture, so we need to maybe zoom stat number 9, see if that fixes it, and there it is. So let's go to trace and let's take a look at the information that we have. So notice that we have 1 for the X value 30, 5 for 35, and so forth. Next, we're going to talk about sampling. So any study concerning populations needs data to be collected. Usually we do not collect data from the entire population. For statistical studies, data from samples is used. The method used to conduct a study is usually something like this. Number 1, specify the population of interest. So let's suppose our population of interest is the students at UWC Costa Rica. Choose an appropriate sampling method. Collect the sample data. Analyze the pertinent information in the sample. Then use the results of the sample analysis to make an inference about the population. And number 6, provide a measure of the inference's reliability. In the next slide, you're going to find some information about random and non-random sampling. So the two main types of sampling are random and non-random. So in random sampling, every unit of the population has equal probability of being selected into the sample. So it's like the lottery. Random sampling implies that chance enters into the process of selection. So random sampling is also known as probability sampling, and non-random sampling is called non-probability sampling. Because every unit of the population is not equally likely to be selected in non-random sampling, assigning a probability of occurrence is impossible. The statistical methods presented and discussed in the IB syllabus assume that the data comes from random samples. So random sampling is obviously more reliable because you choose from the population at random. Whereas if you use non-probability sampling, then you can purposefully skew your results. And that's something that is very common in politics, for example, in suppression polls. In suppression polls, What they do is they choose the samples, not randomly, but by proportions. And then you get the results you expect, so your candidate would look much better than the rival. So we have something called simple random sampling, and it's the most elementary random sampling technique. It can be viewed as the basis for other random sampling techniques. With simple random sampling, each unit of the sampling frame is numbered from 1 to n, where n is the size of the population. Next, a random number generator, it could be a computer program, for example, or a table of random numbers is used to select n items into the sample. So in the case of a study on, say, the population of UWC Costa Rica, we could just pick people randomly by assigning a number to each student and then just randomly picking a sample from that population. In example 7.3, it says, suppose it has been decided to interview 20 students from a school of 659 to form an understanding of their views of a new block scheduling the school wants to adopt. To find a simple random sample, number the students from 1 to 659 and have a random generator choose 20 numbers. The students allocated to the chosen numbers form the sample. So next we're going to take a look at stratified random sampling. In stratified random sampling, the population is divided into non-overlapping subpopulations called strata. The researcher then carries out simple random sampling on each of these subpopulations. The main reason for using stratified random sampling is that it has the potential for reducing sampling error. So for example, if we use the previous method of simple random sampling with, say, the students at UWC, we might have a problem of oversampling boys. Let's suppose that we take a sample of 10 people, and it turns out that 6 of those people are boys and 4 are girls. Now that would not be a good sample because we know that in the school there's about 65% girls and about 35% boys. So this would be a better method of sampling the students from UWC. By doing a stratified random sampling, we could divide the subpopulations into 2 strata, one for boys and one for girls. So with stratified random sampling, the potential to match the sample closely to the population is greater than it is with simple random sampling because portions of the total sample are taken from different population subgroups. However, stratified random sampling is generally more costly than simple random sampling because each unit of the population must be assigned to a stratum before the random selection process begins. So let's take a look at example 7.4, and it says, in FM radio markets, age of listener is an important determinant of the type of programming used by the station. The figure shows a stratification by age with 3 strata, based on the assumption that age makes a difference in preference of programming. This stratification assumes that listeners of 20 to 30 years of age tend to prefer the same type of programming, which is different from that preferred by listeners of 30 to 40 and 40 to 50 years of age. Within each age subgroup or stratum, homogeneity or likeness is present. Between each pair of subgroups, heterogeneity or difference is present. A simple random sample is taken from each stratum. Together, the samples constitute a representative sample of the whole population. So we can see that illustrated in this chart. So next, let's take a look at systematic random sampling. With systematic random sampling, every kth item is selected to produce a sample of size lowercase n from a population of size uppercase N. The value of k, sometimes called the sampling cycle, can be determined by the formula k is equal to uppercase N divided by lowercase n. So it's a simple proportion. If k is not an integer value, it should be rounded to the nearest integer. So 7.5 is an example of systematic random sampling. So it says, given the data in example 7.3, suppose we need to take a sample of 20 students using systematic sampling. First, find K. So K is simply going to be the total amount of students divided by the sample, and this equals 32. So from the list of 659 students, we randomly choose a starting number between 1 and 32. It can be any number. This might be 11, for example. After that, we choose every 30-second number. So 43, 75, 107, etc.